Yeah. In this session, we'll discuss about how to map the poles in S-plane to Z-plane, right? So before going to that, we'll use this the derivation which we have derived in the previous session. That is Z equal to e power ast, right? Where t is sampling time. So you know Z is equal to r e power j omega. That is r is magnitude, and s is equal to sigma plus j omega. If you substitute these two in this expression, what you can get, r e power j omega is equal to e power, our s is this, that is I can write sigma plus j omega into t, right? So this we can write e power sigma t into e power j omega t, right? So if you compare the real part and imaginary part, what you can write, r is equal to e power sigma t is one expression, and from imaginary part omega is equal to omega t. By using these two expressions, we can transform poles in S plane to the Z plane. Now we'll see how to map the poles in the S plane to Z plane. So first of all, take the expression which we had derived in the previous class, that is Z is equal to e power sigma t into e power j omega t. Let us assume you have an S plane. This is my S plane, right? And sigma is on x-axis, j omega is on y-axis, right? Let us assume I have a pole in the left half of your S plane, S1. S1 is, it has a sigma 1 value. You know that all these values are negative, right? -1, -2 and so on. So sigma 1 t plus j omega 1 t. So what is corresponding Z1? Z1 you can write it as sigma 1 t into e power j omega 1 t. In this you can observe that always the sigma 1 is negative value. So the overall e power j omega 1 t, always it is less than 1, right? Suppose if you take a Z plane with a unit circle, right? Unit circle means this r is 1, right? Then where is the location of S1 in your Z plane? Definitely it is inside the unit circle. It will map to inside the unit circle. The same way, take any pole in the left half of S plane, that will map to inside the unit circle, right? You can simply draw like this. Any pole in the left half of S plane lies inside the unit circle, right? Now in the second case, assume you have a pole S2 in the right half of your S plane. So what is S2 now? S2 is sigma 2 plus j omega t, omega 2 t. The corresponding Z is Z2 e power sigma 2 t into e power j omega 2t, right? And once again, sigma 2 value, right? If you observe sigma 2 value for any pole in the right hand side, the value is always positive, right? Sigma 2 is positive here, right? So if it is positive, the overall value e power sigma 2 t, always it is greater than 1. So this pole will take a unit circle, r is equal to 1. This pole maps to outside the unit circle. And similarly, you can write any pole in the right hand side of your S plane will occupy the location outside the unit circle, right? This you can write it like any pole in the right hand side, they'll occupy outside the unit circle. Let us assume we have a pole S3 on the j omega axis. This is j omega axis, j omega 3, assume S3, right? So S3 is equal to, what is a sigma 3 plus j omega 3, where is the corresponding Z3 is e power sigma 3 into t e power j omega t. And you know that sigma 3 is 0. Reason is it is on the j omega axis. So Z3 is 1 into e power j omega t. What it indicates, always the magnitude of Z pole is 1, right? So the S3 is mapped into this. S3 lies on unit circle. So what will happen? This S3 lies on unit circle. Similarly, if you take any pole on j omega axis, where is the location? So definitely these poles are mapped onto the unit circle, right? You can write it like so. In this way, you can, using this impulse invariance method or this relation, we can map h of s into h of z. That is, we are mapping all the poles in s plane to z plane, right?